Imagine controlling a computer, moving a robotic arm or communicating with another device using nothing but your thoughts. At the center of that possibility is a brain implant roughly the size of a coin, packed with advanced electronics and connected to the brain through microscopic flexible threads. These threads contain electrodes capable of detecting the tiny electrical signals produced when neurons communicate. Specialized electronics collect those signals, software interprets them, and the user's intended movement can then be converted into a command, such as moving a computer cursor. But how can something this small, delicate, and complex be manufactured safely? How are thousands of microscopic components assembled into a device designed to operate inside the human skull? And how can flexible threads, thinner than a human hair, be inserted into the brain without damaging important blood vessels? Today, we are entering the world of brain-computer interface manufacturing to follow the process from the first digital design to semiconductor fabrication, electrode production, implant assembly, laboratory testing, and robotic implantation. Neuralink has not publicly revealed every proprietary detail of its current production line. However, its published research provides a detailed picture of the implant's core technologies. Combined with established semiconductor and medical device manufacturing methods, this allows us to reconstruct how a Neuralink-style brain implant would realistically be made. This is how engineers are attempting to build a direct connection between the human brain and a computer. The process begins long before any physical component reaches the factory floor. Engineers first design three interconnected systems: the implant, the microscopic electrode threads, and the surgical robot. The implant must receive extremely weak electrical signals from the brain, amplify them, convert them into digital information, and transmit the data to an external device. At the same time, it must consume very little power and produce as little heat as possible. Excessive heat could damage surrounding tissue, while excessive power consumption would require a larger battery. The electrode threads create the physical connection between the electronics and the brain. Neuralink's N1 system has been publicly described as using 64 flexible threads carrying a combined total of 1,024 electrodes. Each electrode acts like a microscopic listening point. It detects changes in voltage created by groups of nearby neurons. However, the implant does not literally read complete thoughts or memories. It records patterns of neural activity. Computer algorithms must then learn how particular patterns relate to intended actions, such as moving a hand, selecting a letter, or controlling a cursor. Engineers use advanced computer modeling to determine the position of every electrode, conductor, microchip, capacitor, antenna, and power management component. Once the design passes simulation, production can begin. The electronic heart of the implant is a custom application-specific integrated circuit, commonly called an ASIC. Unlike a general-purpose computer processor, an ASIC is designed to perform a specialized set of operations efficiently. For a brain implant, those operations include receiving tiny analog signals from the electrodes, filtering unwanted electrical noise, amplifying the useful signals, and converting them into digital data. The manufacturing process begins with an ultra-pure silicon wafer. Inside a semiconductor fabrication plant, the circular wafer is cleaned before receiving an extremely thin coating of light-sensitive material called photoresist. A photolithography machine projects microscopic circuit patterns onto the wafer. The exposed sections of photoresist are developed, revealing selected areas underneath. Processes such as etching, ion implantation, and material deposition are repeated many times. Layer by layer, transistors, insulating barriers, and microscopic metal connections are formed across the silicon. The completed wafer may contain hundreds or thousands of identical processor dies. Automated inspection systems search for contamination, pattern defects, and electrical faults. Microscopic probe needles then contact test points on each die to determine which processors operate correctly. The wafer is cut into individual chips using a precision diamond saw or laser dicing system. Only chips that pass electrical testing continue to the implant assembly line. The neural threads are among the most difficult components to manufacture. Traditional brain electrodes are often relatively stiff, but brain tissue is extremely soft and moves slightly with breathing, blood circulation, and normal body motion. A rigid implant can create mechanical stress where the device meets the tissue. Neuralink's approach uses narrow polymer threads designed to be much more flexible. Production begins on another clean wafer, but this wafer serves as a temporary manufacturing platform rather than becoming part of the final implant. A thin layer of polyimide or another biocompatible polymer is deposited across the surface. Next, microscopic conductive tracks are created. Published Neuralink prototypes used extremely thin gold traces encapsulated inside layers of polymer. Photolithography defines the path of each electrical conductor. Unwanted metal is removed, leaving narrow tracks that travel from the electrode sites towards a larger connection area. Another insulating polymer layer is added over the conductors. Tiny openings are then created at the locations where each electrode must contact the brain. The result is an extremely thin ribbon containing multiple recording electrodes and microscopic conductive pathways. Published Neuralink research described prototype threads approximately 4 to 6 micrometers thick, with different thread designs ranging from 5 to 50 micrometers in width. At one end of each thread, engineers form a tiny insertion loop. This loop allows the surgical robot's needle to capture, transport, and insert the thread. Because the threads are too flexible to handle freely, they remain supported on a temporary carrier film until the moment of insertion. The exposed electrode contacts are extremely small. A small surface area can create high electrical impedance, making it more difficult to collect clean neural signals. To improve performance, the electrode contacts may receive a specialized conductive surface treatment. Published Neuralink prototypes tested materials including iridium oxide and the conductive polymer PDOT. These coatings increase the electrode's effective surface area without dramatically increasing its physical dimensions. The wafer is placed inside controlled processing equipment, where the coating is deposited only on the required electrode sites. After treatment, automated probe systems test the electrical impedance of every electrode. Electrodes outside the permitted range may indicate contamination, a broken conductor, or an incomplete coating. A single defective connection could remove an entire recording channel. Therefore, inspection must happen repeatedly throughout production. After the thin film structure is complete, the thread array must be separated from its manufacturing wafer without stretching, folding, or tearing it. A carefully controlled release process removes the sacrificial material holding the array to the wafer. The individual threads remain arranged on a temporary support film so they do not become tangled. High-resolution machine vision cameras scan along each thread. The inspection system looks for cracks, damaged electrode contacts, irregular edges, and breaks in the conductive traces. Electrical continuity tests confirm that signals can travel from each electrode to the implant's connection area. The thread dimensions are so small that ordinary manual handling would be impractical. Specialized vacuum tools, precision stages, and robotic transfer systems are required to move the arrays between processing stations. A completed array now resembles a central sensor region surrounded by dozens of long, flexible threads. But it cannot yet communicate with a computer. It must first be connected to the electronic processing system. The sensor end of the thin film array contains microscopic contact pads corresponding to the recording channels. The custom processor chips must be aligned precisely with these contacts. A method known as flip chip bonding can be used for this operation. The processor die is turned face down and positioned above the matching contact area. Machine vision cameras examine alignment marks on both components. The placement system makes tiny corrections, until the contacts are aligned. Controlled heat, pressure, or ultrasonic energy then creates the electrical connection. Published Neuralink prototypes used custom alignment methods and gold stud bumps to position the flexible film before the integrated circuits were bonded. Additional components, including capacitors, control electronics, motion sensors, power management circuits, and communication hardware, are placed onto the miniature circuit assembly. Automated optical inspection confirms that every part is correctly positioned. X-ray imaging may be used to examine hidden solder connections beneath the processor dies. The assembly then undergoes another electrical test to confirm that all recording channels communicate with the processor. A fully implanted device cannot depend on wires passing permanently through the skin. It therefore requires an internal power source and a wireless communication system. A compact rechargeable battery supplies energy to the processors and communication electronics. Engineers must carefully balance battery capacity, physical size, charging speed, and operating temperature. A power management circuit regulates the voltage delivered to each part of the implant. Wireless charging equipment transfers energy through the skin without requiring a physical connector. The external charger must align correctly with the implanted charging system and regulate the energy transfer to prevent overheating. The wireless communication hardware sends processed neural data to an external computer or mobile device. The electronics must work through skin and surrounding tissue while using limited energy. The communication protocol must also protect the connection from interference and unauthorized access. Each wireless module is tested inside equipment designed to simulate the signal-absorbing properties of human tissue. Engineers measure connection stability, transmission range, charging efficiency, battery life, and surface temperature. The human body is an extremely challenging environment for electronics. Moisture and dissolved salts can corrode metal connections and cause short circuits. At the same time, the implant's materials must not release harmful substances into the body. The assembled electronics are therefore enclosed inside a biocompatible protective housing. Published Neuralink prototypes used titanium enclosures with parylene C coatings as additional moisture barriers. The housing components are cleaned inside a controlled environment to remove oils, dust, and chemical residues. The electronics are placed inside the enclosure, while the flexible thread array exits through a carefully sealed interface. Precision welding equipment joins the housing components. Laser welding may be used because it creates a narrow, controlled seam with limited heat exposure. The enclosure is then checked for microscopic leaks. A helium leak test can reveal openings too small to detect visually. The sealed unit may also be submerged in controlled solutions and monitored over time to determine whether moisture can penetrate the housing. Only implants that remain sealed and electrically stable move to the next stage.
Testing an implantable brain interface is far more demanding than testing ordinary consumer electronics. The completed device is placed in an automated test fixture that simulates electrical signals similar to those produced by neurons. Every channel must detect, amplify, and digitize these simulated signals accurately. Engineers measure background noise, signal gain, data loss, processor temperature, wireless stability, and power consumption. The flexible threads undergo mechanical testing. Machines repeatedly bend and move the threads to study how they respond to long-term microscopic motion. Accelerated aging chambers expose test devices to elevated temperatures and controlled solutions. This helps engineers estimate how the materials and seals may behave after extended implantation. The battery is repeatedly charged and discharged. Wireless communication is tested under different positions and levels of interference. The implant must also continue operating safely if an electrode fails, communication is interrupted, or the battery reaches a low charge. Software safety systems monitor temperature, voltage, and unexpected electrical activity. If a reading moves outside its permitted range, the system can reduce power or shut down selected functions. Once the implant passes functional testing, it enters the medical device preparation stage. Microscopic particles and manufacturing residues must be removed without damaging the delicate threads. The implant is cleaned using tightly controlled processes compatible with its polymers, electronics and coatings. It is then packaged inside a sterile barrier system designed to protect it during transportation and storage. The sterilization method must destroy microorganisms without degrading the battery, electrode coatings or flexible thread materials. Each package receives a unique identification number linking it to manufacturing records, component batches and test results. This traceability allows engineers to investigate the complete production history of an individual implant if a problem is later discovered. The finished implant is now ready for the surgical team. But manufacturing the implant is only half of the challenge. The threads are far too flexible to be inserted accurately by hand. That requires a specialized neurosurgical robot. Before surgery, medical imaging and surgical planning software help identify the target area of the brain. For applications involving computer control, the target may include regions of the motor cortex associated with intended movement. The robotic system maps the exposed surface of the brain and identifies visible blood vessels that should be avoided. Its insertion head contains precision cameras, specialized illumination, a microscopic needle and a supporting pincher mechanism. The needle is designed to pass through the tiny loop at the end of an electrode thread. Computer vision locates the loop and guides the needle into position. The robot then carries the thread towards the selected insertion point. A surgeon remains responsible for the procedure and can review or adjust the planned locations. Published Neuralink research described an automated mode capable of inserting 6 threads, containing 192 electrodes per minute, although actual surgical speed can be reduced when additional care is needed to avoid blood vessels. During the procedure, the neurosurgeon exposes the selected area of the cortex and prepares an opening for the implant housing. The R1-style surgical robot positions itself above the brain. The robot selects the first flexible thread from the implant array. Its microscopic needle enters the thread's insertion loop and lifts it from the supporting film. Machine vision cameras examine the cortical surface and confirm the target location. The needle advances into the tissue, carrying the thread to a programmed depth. It then retracts rapidly, leaving the flexible electrode behind. The process repeats for the remaining threads. Because every thread can be positioned separately, the robot can distribute the electrodes across the target region while attempting to avoid visible surface blood vessels. Once the insertions are complete, the implant body is secured inside the opening in the skull. The scalp is then closed over the device, leaving the implant concealed beneath the skin. After recovery, the implant is activated and connected wirelessly to an external computer. At first, the system does not automatically know what every neural pattern means. The user may be asked to imagine or attempt specific movements while the implant records activity from the motor cortex. For example, the user might imagine moving a computer cursor to the left. Software compares the recorded neural activity with the requested movement. This process is repeated many times. Machine learning algorithms begin identifying patterns associated with different intentions. As more training data are collected, the decoder becomes better at translating neural activity into commands. The user also learns how to control the interface more consistently, creating a partnership between biological learning and machine learning. The final output can control a computer cursor, select on-screen buttons, enter text or operate compatible digital equipment. This is where the implant becomes more than a collection of silicon, gold, polymers and titanium. It becomes an information bridge between the activity of the human brain and the digital world. Manufacturing a Neuralink-style implant requires several of the world's most advanced industries to work together. Semiconductor factories produce the custom processors. Thin film production lines create flexible microscopic electrodes. Medical device engineers package the electronics inside a biocompatible enclosure. Automated laboratories test every recording channel, battery and wireless connection. Finally, a precision surgical robot places the flexible threads into carefully selected regions of the brain. The technology remains experimental, and important questions surrounding long-term safety, reliability, privacy and accessibility have not yet been completely answered. But for people living with severe paralysis, brain-computer interfaces may offer a new way to communicate with computers and regain a level of digital independence. And as implant production, robotic surgery and neural decoding software continue to develop, the boundary between the human nervous system and machines may become increasingly difficult to see. Would you allow a computer chip to connect directly to your brain? Tell us what you think in the comments. Subscribe to How Factories Made It for more incredible videos about artificial intelligence, robotics, semiconductor factories, supercomputers and the technologies shaping our future. Thank you for watching.